And we're actually going to start before we jump into composition combination functions or function operations. So starting out with that little review, you can see in this graphic here, this is just like a snapshot from your textbook. That's centered. Okay, so just like you would combine any real numbers with addition, subtraction, multiplication, or division, you can also combine functions. Okay, so the notation for those operations look like this. Okay, so if you have two functions that we'll call f and g, okay, if you want to combine them with addition, okay, you're finding the sum. Okay, it can be notated here like this, where it says f plus g of x. That's how you would read that. F plus g of x. Okay, that is the same thing as writing them separately with the addition sign in between. So f of x plus g of x. Okay, so those mean the same thing. Now, if you are doing the sum of two functions, if you're finding the sum, then you're simply combining like terms. That's all that is, because you end up with two functions, and if they have anything in common, it's literally just combining like terms. Okay, now when you go to find the difference between two functions, okay, it's the same concept. We read this the same, f minus g of x or f of x minus g of x. The only difference would be that this subtraction sign, this minus, would have to be distributed to all terms within the second function, the function being subtracted, in this case, g of x. Okay, so I'm going to just accentuate that that needs to be in parentheses when you write out what the function is, because that minus has to get distributed. So I'm going to just make that little side note to make sure you understand that you distribute the negative first. Then you do the combined like terms. Okay, so both of these are combined like terms, but here you have to distribute that negative first. All right, now for the product, okay, so this is a solid dot here for multiplication. So that would be read as f times g of x, which is the same as writing it as f of x times g of x. Okay, and depending on what the terms are in those functions, you're probably going to have to do some sort of distribution. Could be double, could be triple distribution, depending on how many terms there are. Okay, but lots of distributing and then simplifying, combining like terms. Okay, for quotient, f over g of x or f divided by g of x could also be written as f of x over g of x. Now this one has a stipulation. Okay, you have to restrict the domain. Okay, so this piece right here, g of x cannot be 0. Why is that? Yeah, it's in the denominator and you can't divide by 0, right? Okay, so there has to be a restriction in the domain to account for that denominator. Okay, so there's going to be a domain restriction for this one. When you get your combined function, your new function, your quotient, you will have a domain restriction. Okay, because that denominator cannot be 0. So for each new function, okay, the domain is going to consist of all of the x terms common to both of the original functions. Okay, so when you do the combining, okay, it's what was the domain of the original two functions, f and g? Okay, what did they have in common? What was the overlap in the domain? And that'll be the domain of the new combined function, except for quotient. Quotient is the special case where it can be more restrictive than the original true, okay? The domain of the quotient can be further restricted, okay, because of the denominator, okay? And we're going to look at that in this practice, these examples that we're going to do here. Okay, so we have defined for us f of x, g of x, and h of x. Okay, so I've got three functions. I'm going to try and color code those for us. So 1, 2, 3. Okay, so we want to do a sum, difference, product, and quotient of some sort using these three functions. Okay, so to start, I'm going to rewrite from this format to show the functions individually. So f plus g of x just means it's the f of x function plus the g of x function. That's all that means. Okay, so that means I'm going to have my f of x function, which I'm going to write here, and I'm going to have to add my g of x function to it. Okay, so that's x squared plus 4x plus, and then the g of x function is the square root of x plus 2. Now, I would get in the habit of whenever I'm inputting a function of just putting it in parentheses. Just in this particular example with addition, it doesn't make a difference. We're just going to drop the parentheses because there's nothing to simplify inside them. There's nothing to distribute or anything like that. Okay. But for other ones, for when we do difference and product, those parentheses make a difference. Okay. And you could make a mistake if you didn't have the parentheses there. So I would just get in the habit of always having them. And then if I don't need them, like here, I just say, okay, I don't need them. They're dropped. Okay. Now looking at all the terms, I have a squared term. I have a linear term. I have a radical term. Can I combine any of those together? There is nothing to do here to simplify this. There's not one single thing I can do. So my final function, my combined function, the sum, is that. That's it. That's as much as I can do. Okay. But the second part of this asks us, I guess, oh yeah, I can. I want a little lighter purple so it doesn't look black. There we go. Okay. This asks us to find each function and its domain. Okay. So looking at the combined function, its domain will consist of the overlapping domains of f and g. So let's go back and look at these original functions and list their domains, okay? Because we're gonna use those for all four of these. So what type of function is f of x? Okay, and so what would that domain be? All real numbers. The domain of the quadratic is all real numbers. Okay, what type of function is g of x? Square root or radical function. Now that one does have a restricted domain, doesn't it? The parent function for the quadratic is normally 0 to infinity for the domain because it starts at the origin and shoots out into the right in quadrant 1. Okay, if you can visualize that. But what type of transformation has taken place here? That's to the left too. So instead, our domain shifts to the left too. So if it was 0 to infinity, now it's -2 to infinity. Because if I plugged in, and I can include the -2, that should be a bracket. Because if I plug in a -2, that's 0. The square root of 0 is 0. We're good. It exists there. But if I try to plug in something less than -2, such as -3, I end up with a negative, and I can't take the square root of a negative. It doesn't exist over there past that -2. Okay, what about the third function, h of x? What type of function is this? linear. And so what's the domain? All reals. So the only one of the original three functions that are defined for us that has a restricted domain is g of x. So here, this domain of this combination function will be where these two domains overlap, which is just the -2 to infinity, right? That's the x values that those domains have in common. So that's the domain. Now for this f minus h of x, that can be written as f of x minus h of x. Okay, and we're going to make those substitutions. Okay, so I'm going to write out the f of x function. And then I'm going to write out the h of x function. Okay, and I am subtracting those. Okay, so the f of x function is x squared plus 4x. I'm going to put it in parentheses. And the h of x function is 3x minus 5. Now this time, those parentheses do matter, don't they? It makes a difference because that negative has to be distributed. Okay, so I distribute the negative. So I've got x squared plus 4x. I can drop those first parentheses, nothing to simplify. And this becomes minus 3x. And then that becomes plus 5. So when I combine like terms here, I have x squared plus x plus 5. Are we okay with that? What are the domains of those original two functions? F and h? Both are all reals. So their combined domain is all real numbers. And it makes sense. This is a quadratic, right? Which should be all real numbers. All right, the product. When we multiply f times g of x, again, that can be written as f of x times g of x. I'm going to write those functions out again. So that's x squared plus 4x times the square root of x plus 2. So f of x plugged in here, and g of x got plugged in here. Well, when we're multiplying these together, what should I do? I have to distribute, right? So this radical, the square root of x plus 2 is going to get multiplied by both of the terms in the f of x function. So that would be x squared, square root of x plus 2, plus 4x times the square root of x plus 2. There's nothing else I can do there to simplify that. That's what we've got. We stop there. Now looking at their domains, the original functions f and g, again, have the same overlap as they did in this one. So the domain would be -2 to infinity. All right, the quotient, yes. So when to cancel out a square and a square root, they have to be applied to the same term. This square is being applied to this x, and this x plus 2 are what are the radicals being applied to. Now, if that squared had, for instance, been put here, like if you were squaring a square root, then yes, those would cancel, but not in this case. Does that help? Okay. All right. Now here we've got h over f of x. So again, that can be written as h of x over f of x. So I'm going to write that out. F of x is in the denominator. H of x is in the numerator. So that is 3x minus 5 over x squared plus 4x. So what type of function has this created? Rational. You've got x in the denominator. So even though these are the same two functions as this above example, and we said, oh, well, they're overlapping domains, all real numbers, this one will not be all real numbers because now it's rational and our denominator cannot equal 0. So there will be an additional restriction, even though the original functions that we used did not have restrictions. Okay, so when we go to look at this for our domain, what cannot happen when we have a rational function? 0 in the denominator. That doesn't mean x can't be 0. It means when I solve the denominator, it cannot be 0, right? So to figure out what x values would make that 0, you set the denominator equal to 0 and solve for x and figure out what x values would be the restrictions. What can x not equal? If you want to put a not equal there to help you understand we're trying to figure out what x cannot equal, that's fine. Okay, so to solve this, I would factor. Okay, so I can take out an x. Okay, and then I would split and solve each factor. So this means x cannot be 0 and x plus 4 cannot be 0. So x cannot be negative 4. So x cannot be 0 or negative 4. Does that make sense? So for my domain in interval notation, that would be negative infinity to the negative 4, union the negative 4 to 0, union 0 to infinity. Does that make sense? There's a gap at negative 4 and 0. The function does not exist at those two values. An alternate way to write that would be to say it's all real numbers except for negative 4 and 0. It's everything, but x cannot be negative 4 or 0. But this is how it would show in interval notation. Questions about combining functions. Function operation. Add, subtract, multiply, divide, two functions. All right, good. Now, the next thing we're going to look at then is the composition of functions. Okay, so if you take a function, y equals x minus 3 squared, for instance, okay, this combines two different functions. Okay, if you look inside the parentheses, x minus 3, that's a linear function. Okay, but if you look at squaring a base value, your x term, that's your quadratic function. So this is a combination. A linear function has been input into a quadratic function. Y'all see that? Does that make sense? So composition is not add, subtract, multiply, divide. It's inputting functions into each other. Okay, so this is another graphic. This key concept comes straight from your textbook. It says the composition of a function f with function g is defined by, so this is the format. This is how you may see it written. So this, I'm going to zoom in so you can see this bigger. This open circle is very different. Oh, gotta scroll over, it's cut off. Then this dot here, this closed one. Okay, if it's a point like this, that's multiplication. Okay, but when it's written this way with the open circle, okay, this is composition. Okay, and so the way that you would read this would be f of g of x. And it can be written this way, f of g of x. Okay, so both of those formats are correct for a composition. Okay, and this shows, okay, your f is the outer function. Inside it, you're inputting the g function, and inside the g function, you're inputting x. So x is the individual value input into the g function, and then that output, what you get when you calculate that, is input into the f function. Everybody good with that? Okay. And this isn't brand new. You did this in Algebra 2, so hopefully you kind of recall that. All right, so we're going to try that with this next example. We want to find f of g of x, g of f of x, and then f of g of 2. Oops, don't need that. Okay, so the first thing I'm going to do is rewrite these without in the other format, because I think it's easier to interpret. So f is the first function, so that's the outer one of, and then g of x is going to be on the inside. Okay, so that's what that means. So I'm going to go ahead and rewrite this one. This is in reverse. This has g on the outside and f of x on the inside. And then this last one, it's the f on the outside, just like the top one, but they're giving us a specific value to input. Instead of just x, they want us to specifically input a 2. Okay. All right, so I'm going to color code again. Let's do f of x in blue, g of x in pink. Okay, so for this first one, the g of x is the input. You're putting it inside the f function. You don't have to write it this way, but if you wanted to, you could totally replace g of x there with x minus 4. They're telling you to have x minus 4 be the input to the f function. Okay, your input goes in place of x. So they're saying come right here and replace x with x minus 4. Okay, so that is x minus 4 squared plus 1. Okay, so then I'm ready to simplify after I've actually done the inputting. So this is the g function inside. I'm going to kind of color code. I'm going to do this so that it's around it. So you can see that pink is input inside the f function. I don't know if that helps, but the g is going inside the f function. All right, so then to simplify this, I would have to do x minus 4 times itself, and then the plus 1. Okay, so to simplify this, I would FOIL. Okay, first, outer, inner, last. So x times x is x squared. X times negative 4 is negative 4x. Negative 4 times x is negative 4x. And negative 4 times negative 4 is positive 16. And then you've still got the plus 1. So then you can combine like terms. We've got the two x terms and the two constants that can be combined. So that reduces down to x squared minus 8x plus 17. Feel okay about that one? Okay, so in reverse of that, I would be inputting the f function, which is x squared plus 1, inside the g function. So this time, the g is the outer function, and the f function's going inside it. So the g function is x minus 4. And in place of the x up here, place of the x, we're inputting x squared plus 1. Okay, so the blue this time is the inner, and the pink is the outer. Okay, so reverse of the previous one. So this one's a little easier to simplify. There's nothing to do in parentheses, so they can be dropped. So then you just can combine your plus 1 and your minus 4. So that just comes out to x squared minus 3. Did those come out the same? Are those the same expressions? No, obviously not. Okay. That's a clue to you that should clue you in that f of g versus g of f is very different. That is not the same thing. You should not get the same answer. If you're asked for one, you can't choose which way to do it. Okay, they are different. Okay, you get different answers. Everybody clear on that? Okay. The only time if you did an inverse or a composition function like this and they came out the same would be if they were inverse functions and they would both come out to just x. Right? Okay. All right, now the bottom section, the third part of this is asking you to specifically input a 2 into the f of g function. So you have two options on how to solve this, and I'm going to show both, and then I'm going to talk about why I prefer one over the other. Okay, so one option is we have already found f of g of x, haven't we? At the very beginning, right here. We said f of g of x is x squared minus 8x plus 17. So what this question is asking us to do is to replace the x with a 2. Okay, so if I do it this way, f of g of 2, I simply plug a 2 in for x and solve. Okay, so 2 squared is 4, minus 8 times 2, 16, plus 17. So that comes out to 5. I'll scroll up a little bit so we can see that. Okay, are we okay with that method to solve that? Okay, now the other option, I'm going to split this box and show the other option over here. Okay, or we can do it this way. F of g of 2. Okay, I'm going to call this side working inside out. Okay, this way you could label this method as using the composition, or composite, I should say, using the composite function that we already found versus working inside out. Okay, so working inside out, I'm going to scroll back up so I can see the original functions here. Working inside out just means, literally, work the inside first. Okay, so work the inside. So I'm going to ask myself, what is g of 2? Okay, well, g of x is x minus 4. So it's 2 minus 4, which is negative 2. Okay, so we just found out that that's negative 2. Do y'all agree? So that means we're inputting a negative 2 into the f function. So now the outer function is the f function. So f of negative 2, the f of x function was x squared plus 1. So it'd be negative 2 squared plus 1. Because we input the negative 2 here. And that also comes out to 5, doesn't it? Which way did you like, but if looking at both of those options, which way, if you had your choice, if I tell you solve it however you want, which way would you do it? First one? Anybody choose the second? Depends on the equation. Yeah, I think for this one, this seemed like a lot less work because this was a trinomial. So you had to plug the x in a couple places to solve. So it does kind of depend on how complicated your composite function is, maybe on what your preference would be. But I will tell you right now, my preference is always this one. Now, that does not mean you cannot do the one on the left. You can, because it gets you the same answer. Okay, you're doing the work correctly. It gets you the same answer. Okay, any ideas on why I might prefer that method? That's exactly right. Okay, so this is a 3-part question. Okay, the first part required us to find f of g of x. If I answer the third part using that answer, if I got the first part wrong, if I made a mistake up here, I'm getting part 3 wrong as well, aren't I? Whereas if I choose this method, if I got part A wrong, I could still get part 3 right. Y'all see that? So that's why this is my preferred method, but that doesn't make this wrong. You can do it this way. You just you have to be very sure you've done your composite correctly. Y'all good with that? Okay. So we've got about 9 minutes, 10 minutes. I want you to try the first 2 practice on the back. And then tomorrow in class, we'll be going over, we'll check those 2 and then go over some of the others. There's 6 problems here. You do not have to try them all right now. I want you to try the first 2 right now. We will do that tomorrow as well. I had said we would do that today and I forgot. You're the first person to remind me. We'll go over last week's quiz tomorrow. I'll pass it back out for y'all to go over. I'll put that on the board so I remember. And if I forget, somebody remind me at the beginning of class. Thank you. All right, so just do these first 2 practice, try those on your own. We'll look over those, check those tomorrow, and look at some of these other practice and go over your quiz from last week tomorrow.